Good morning to all present. So I introduce myself as Samanpreet Kaur. I'm currently working as Associate Professor in the Department of Soil and Water Engineering, Punjab Agriculture University, Ludhiana. I'll be delivering the talk on managing groundwater demand through surface water and wastewater treatment. This work was done in the Tigris project under the flagship program 5. So this study basically pertains to Indian Punjab, which is one of the smallest state in the country, and it occupies 1.53% of the total geographical area. And however, this 82% of the state total geographical area is used for agricultural activities, as you can see from the net zone area figures. And just to give an overview of how the agriculture development has taken place in the last 4 decades in the state, the slide shows a comparison of the data of 1966 and 2019-20. So in 1966, we can clearly see that the net irrigated area as a percent of net sown area was just 58%, and now entire area in Punjab is irrigated, and the cropping intensity has risen from 133 to 190. That means we are taking at least two crops per year. And if we look at the source of irrigation, the tubewell irrigated area has increased from 24.5% to 71.1%, and the canal irrigated area, on the contrary, has decreased from 32.9% to 28.9%. And if we want to study in detail the cropping pattern, now the area is predominantly rice wheat with 10 time increase in the rice area, and double figures in the wheat area. And if you look at the yield of the rice and wheat, it has approximately increased 3 times. Like it has increased from 1322 kg per hectare to 4034 kg per hectare. And in case of wheat, we are seeing an increase from 1520 kg per hectare to 5004 kg per hectare. And looking at the rainfall in Punjab, it has been showing a decreasing pattern during the recent years, with a more number of years showing a deficient rainfall, which is resulting in more irrigation demand. And as already discussed, that the canal irrigated area has reduced, the rainfall has decreased, so the number of tube wells have increased. That means the dependency on groundwater has increased over the years. And if we look at the figures from in 1980, only 0.6 million tube wells were there. Now it is 1.47 million tube wells are there in the state. So all this is leading to unsustainable groundwater use. The map shows that the water table depth has decreased in the entire state, and we can see that the area which was around 70% between 3 to 10 meter, but now it is only 30% that is between 3 to 10 meter. And we are seeing this region having the deepest water tables, uh, this area. So we have selected this area for our research purpose. So we have selected this Sarhand Canal tract region for our research purpose. And in this, we can see that water table is quite deep. And but this area has a extensive canal network in that. However, these canal are more or less, they are transporting water to the southwestern districts or to the neighboring states, that is Rajasthan and Haryana, but they are not delivering much water in the tract itself. And however, there is certain recharge that is possible from these tracts, and we can see that the elevation of this region varies from 856 in the eastern part, and it is about 192 meter above the mean sea level in the western side. So it is having a varied topography. So the basic purpose of our research was that with the current cropping pattern, how can we make our groundwater levels sustainable? This means that we are not reducing the demand, but we are reducing the groundwater use when enhancing the surface supplies. So for this, we calibrated and validated a numerical groundwater model, which was our first objective, and then we use the same model to predict the impact of various pumping management strategies and the water management strategies on the groundwater level, which was our second objective. So this is the entire flow process, in which first was the identification of the tract. We selected the Sarand Canal tract firstly because the water table is declining very fast in this region. Secondly, the reason for selecting this tract was that the tract had a hydrological good hydrological boundaries on all the sides, so it was very easy for it was very easy for us to develop a groundwater model. So for this, we conceptualize the model and discretize the model using the secondary data. We took the data of the aquifer parameters, we took the data of the lithology, we took the data of the climate, and then the canal network, and what were the groundwater abstraction rates, and what was the recharge and the draft. We estimated these recharge and draft values using the Central Groundwater Board norms, and then we simulated the groundwater model. The model was calibrated and validated, and this model was used for uh, evaluation of the different pumping scenarios and the irrigation conditions. So we had in total 12 strategies, in which there were 4 pumping scenarios and 3 irrigation conditions. So I'll explain these conditions and the scenarios. The pumping scenarios which we considered were that the current pumping rate will continue till 2030. In the scenario second, we considered that the a number of tube wells will increase in accordance to the past pumping trends by taking the data of the last 5 years. In the third scenario, we assume that we'll have the current pumping rates, but will increase the canal water supplies by 10%. As we have already told you that the canal water supplies are less in this region, and the water is being transported to the southwestern districts and the neighboring states of Rajasthan and Haryana. And in the fourth scenario, what we considered was, as we are increasing the canal water supply, accordingly we are having some sort of policy that we can decrease the groundwater abstraction by the similar percentage. And in the irrigation conditions, we considered because there are about 42 STP plants in the region. This is shown in the slide by the brown color dots. So there are about 42 STP plants. Presently, the water is not being used for irrigation. So if we can use this water for irrigation, the water that is obtained from the STP plants, if it can be used for irrigation, then how it is going to impact our groundwater levels. So the 3 conditions were assumed based upon this. One was normal irrigation when there is no augmentation. Second condition was that we are augmenting the irrigation with the treated wastewater from the existing sewage treatment plants. And third condition is because these plants are created for they are treating the wastewater, but the treatment capacity is very less as the potential capacity of these plants. So if these plants are fully operational, and if they are discharging the treated wastewater to their potential capacity, what impact they will have on the groundwater levels, that was considered. So how did it make sense that we are going to increase the canal water supply? Basically, if we look at the data of 1970, 1990 and 2018, the canal irrigated area, basically if we look specifically at 1990 and 2018, we can see that it has decreased by 125,000 hectare, which is actually 10%. So that 10% figure makes the sense here of uh, augmenting the groundwater with canal water. So once the model is calibrated and validated, we had fed the different alternative scenarios to the model, and we to see the impact on groundwater levels. So on the uh, x-axis we are seeing this 1, 2, 3 and 4, these are the pumping scenarios, and on this side we are seeing the irrigation conditions, that is no augmentation, irrigation condition B, augmentation with existing treated wastewater, and irrigation condition C, augmentation with potentially treated wastewater. So if we look at all these scenarios and conditions, we see that in the business as usual scenario, which is the basically the scenario 2, the water table will fall from the present water level of 23.20 to 44.7 meter, and even if we are using the treating water, we are able to control the water up to 42.4 meters. So in the worst case, this is the worst case scenario in which the water table is going to fall. So these values, these are giving us the future condition of 2025. The yellow color shows the future condition of 2025, and the blue color shows the future condition of 2030. So, and if we look at, if even if we are not allowing more number tube wells, then also we are seeing the fall, that is the water table will fall by approximately 5 meter from the actual. So but if we are enhancing the canal water supplies, and even if we are not decreasing the groundwater abstraction, then also we are seeing that the water table is falling beyond the present condition, that is 23.2, and we can reverse the trend by using the condition 3 and condition 4. Here we can see that the trends have reversed. So that is basically when we are using both the strategies, that is we are augmenting the irrigation supplies with the canal water, and similarly we are augmenting some of the supplies with the treated STP water. So we have a scope where we can totally reverse the trend if we use the our STP to the potential to the potential, to their potential values. So in all, what we can say, that is if we are going for business as usual of the groundwater abstraction, there will be a decline of 21.49 meter from the present level by 2030. And even if we are going for restriction on the development of new tube wells, which was a scenario 1, there will be still a decline of 5.96 meter by 2030, and an increase of 10% canal water supplies and corresponding decrease in groundwater abstraction can reverse the falling trends, and augmentation of irrigation supplies with the treated wastewater from the existing STPs, they can really improve the groundwater levels by 3 to 6%, and all wastewater generated in future, if it is treated, the groundwater levels are expected to increase by 8 to 11%. So the take from the study is, the first is that the new tube wells for farm irrigation should be avoided, and the surface water exploitation should be promoted. That is the takeaway from the study. And for this study, uh, there were contributors from Soil and Water Engineering, Punjab Agriculture University, Ludhiana, and Makis and Dr. Jagjit Singh Sarai from University of Cambridge. And I would also like to thank Dr. Nishikant Mishra from Department of Business, Law and Politics, University of Hull, United Kingdom. Thank you.